Okay, so we take a look on this R square, so generated by the regression analysis. And so R square is quite good. It's not very good, but it's quite good. It's 0.6083. So it's the same as before when we generated by plotting. But basically they are all generated by the Excel, so that should be the same. And okay, so let's take a look on the R square F measure. So F is 12.4243. So the significance level, which is actually the probability of the F measure, is 0.007. So this is actually a very, very tiny probability. So that basically means the R square based on the R measure equal to 0 cannot be accepted. So we're gonna reject the non-hypothesis. So the non-hypothesis is that R square is 0. Alternatively, R square is not 0. So a very tiny probability means R square is significantly not 0. So that means, okay, so the regression analysis is basically a quite good result. So degree of freedom for regression, because we only have one x, so one variable. So degree of freedom for regression is 1. And the total degree of freedom is the total number of data minus 1, because we only have 10 data sample. 10 minus 1 is 9. So regression degree of freedom is 9 minus 1 is 8. So this is sum of square and mean square. So mean is actually using sum of square divided by degree of freedom. So this is basically the same because the degree of freedom is 1. So for the residue, because the degree of freedom is 8, so we're using sum of square. It's roughly 80.72 divided by 8. So it's roughly 10.009. So this is actually a mean square. So we're using mean square of regression divided by mean square of the residue. So we got F square, F measure. So F measure generates a very tiny probability. So and that basically means R square is significantly not 0. Okay. Okay. So and let's take a look on the covariance. So we only have a 1x, so the covariance is just the number of stalls, so there's a 0.31. Let's take a look on the p-value. So the p-value for the covariance is very tiny, it's 0.00779. So a very tiny p-value means the non-hypothesis for the covariance should be rejected. The non-hypothesis for the covariance is actually the covariance is 0. So now we have a tiny probability we reject the non-hypothesis. So that basically means we accept the alternative hypothesis. So the covariance is not 0. So that means the number of stalls has a significant impact on the sales volume. So this is a good regression analysis. So we have a significant and independent variable. And we have pretty okay R square. So, and that means the X can explain roughly 61% of the Y, which is the sales volume. That's a pretty interesting result. Okay, so this is the first linear regression example. In this example, we only have a 1X. And the next example, so we're going to have a number of different axes. So this is data from a number of students. So we have many different characteristics for students, and we would like to using so many different characteristics of one student to explain the Y, which is the chance of admit. So this is a probability of the students can receive an offer from a university. So this is actually a linear regression for a number of different variables. So we would like to run a linear regression by using a data analysis and regression. So I will basically choose the Y, and so I want to delete this. So Y is the chance of admit. So I want to select all the Y, and then I delete this. So I select all the X. X is from the GRE to the research. So this is all the data in here. So we have the X. So because the first row of all the data is the name of every column. So this is a label. So the output range is, I want to put the data to here, so result to here. So I click OK. So okay, fine. So I generated the regression analysis. Cool. Let's take a look on R square. Wow, that's pretty good. R square is actually 0.82. So that basically means if we use all the X to explain the chance of admit, so basically all the X can explain roughly 82.19% of the chance of getting an offer of the students. So that's pretty good. So the F value is huge. And so the probability of F value is very, very, very tiny. It's basically 0. So so that basically means the R square is very, very significant and higher than 0. And the regression, degree of freedom of regression, because we have 1, 2, 3, 4, 5, 6, 7. So 7 independent variables. So the degree of freedom of the regression is 7. Because in total we have 500. So let's take a look on the one. So okay, so last one 501. So because the first row is the name. So basically we have 500 data. So the total degree of freedom is 500 minus 1 is 499. So the residue degree of freedom is 499 minus 7 is 492. Okay, so we can basically have calculated the sum of square and mean square. So we can calculate the F using the mean square of the residue divided by of the regression divided by the mean square of the residue, which is very tiny. So we got a huge F measure. So and this is basically a proof for R square is basically significant. And let's take a look on the coefficients. So we have 7 coefficients, and let's take a look on the p-value. So p-value is quite different because we know if the p-value is smaller than 0.05, so that basically a good result. So that means that independent variable is significant to the y. So we have this one, that's very tiny, and maybe this one, and this one, and this one. So we got basically 5 and variables, and their p-value are smaller than 0.05. That means those 5 variables are significant to the y. But the other 2 universal ranking, so this is very high. So that basically means this variable is not significant, and SOP is not significant. Okay. So we have done this regression with pretty good results. We got high R square, and we got very significant independent variables and 5-1. So those are pretty good. So that basically means, yes, we can using maybe those 5 variables to explain the chance of admission. So for students. So this is a pretty interesting result for linear regression. Okay. Okay, so let's getting back to here, so to the slides. And we've done the linear regression, because that is the last slides. This is the students and results for the linear regression. Okay, now let's move to the next topic called panel regression. Okay, what is panel regression? So why do we need to use panel regression? So we're going to take a look on several examples of a panel regression. So let's think about what about we would like to investigate the effect of education on the a person's income. So if we collect some data, so we might collect a number of different people, many different peoples, and for many different years. So for one people, so we can collect the salary for maybe 10 years, but at the same time we can have say 1,000 different people. So now we have basically 2 dimensions. One dimension is the time, so we have 10 years data, and every year we actually have 10 maybe 1,000 different individuals. So we have different people and across different years. So basically this is 2 dimensions for the data. So similarly, we can investigate the effect of the income on the average income on the saving. So this is what if we would like to investigate on the country level. So we can calculate the average income for a country. And so we can collect loads of different countries. For example, we can collect 100 countries across the last 20 years. So we can have a data across the time, at the same time, across different individuals, different countries. So this is a 2 dimensions, time and different individuals. So this is the characteristics and for the panel data. So panel data has the information of the individual behaviors across 2 dimensions. Across the individual, different people might have different behaviors, and for one particular person or particular people, and his behavior could be different across different time. So they have cross-sectional and time series dimensions. So usually we're using M to represent the different people, so different individuals, and T represents the time periods. So we and different individuals across T different time periods. But sometimes, so we might have M individual people's data, and every individual, so their data is across T time periods. But sometimes we don't have we don't have all the we don't have the data for all the individuals across the same time period. So that's actually called unbalanced data. For example, we have a 10 years data, but some people will only have 10 years, some people will only have 5 years, or some people have 6 years. That could be quite different, but we have 1,000 different individuals, 1,000 different people. So, but not every individual can basically have their data across the 10 years. So this is actually unbalanced. Okay. So usually when we are trying to do panel regression, we have 2 assumptions. So the first one is we assume for every individual, so their data across the time has correlation. But the data across different individuals are independent. So individuals are independent, but for one individual, so their data over the time are correlated. So this is a 2 assumption for panel regression. Okay, so we have actually sometimes the short panel and long panel or both panel. Short panel means we have a very short time, but we have many different individuals. So this is usually happen when we are trying to analyze the company data. So maybe we can analyze a company across the last 10 years, but we can't collect the data for 2,000 companies. So this is a very short time period, but this is very wide. We have 2,000 companies across 10 years. Sometimes we only have several individuals. For example, we may have like 20 stocks, but we can have high frequency data. So across the last 10 years. So but actually the stock prices is not, the interval for stock prices is not just a year. So the stock prices interval could be just a minute. So every minute we have a stock price. So that means a day we can have thousands of different the stock prices. So across 10 years, so we have millions of prices, but we only have 10 stocks. So we have a very long time period, but we only have very few individuals. Sometimes we have both a very long time period and many individuals. So this is both panel. Okay, so and think about if we have a panel data. So we might have a number of different variables. So and probably sometimes we could have varying independent variables. So for example, for a person, so the person's income could be different across time, could be different across individuals. So that could be very different across both 2 dimensions. But sometimes we have like a gender, race, or education. So this is actually the fixed one for one individual over all the time. But this could be quite different across different individuals. So different individual has different, gender, different race, different educations. But for one individual, for most of the time, so the gender is fixed, race is fixed. Once you finish your education is fixed. But sometimes, we have individual invariant variables. So that basically means for every single person, so the variable is the same. But the variable is basically change over the time, like economy trends or time period, time trend, or unemployment rate. So this is a huge macroeconomic variables. So this is the same for all the individuals because this is the whole world variable. But this could be different over different time. So this is several different types of individual independent variables. Okay, and now let's try to define several, variations. So we have two dimensions, so we might have quite different variations. So the first one we define overall variation. So overall variation is just a variation over the time and individual. So we don't care about, so this is we don't care about individual, so different person or different time. We just care about the differences across different data. So this is overall variation. And also we can have between variations. So this is the variation between the individuals. And also we can have the within variation. The within variation is variation within every individual over the time. Okay, so let's take a look on this table. So this is, I think, a very interesting table, and it's a very good example for, the panel data. So the first two columns is called ID and time. So this is usually the way we are going to organize the panel data. So usually we're using ID to identify different individual. We're using time to identify different, time period. So let's look on the first column. So we're using I to represent ID, and the first three rows is 111. So that means we have the first person, the ID is 1, and for the first person, so we have actually the data over 3 time period 1 to 2 to 3. So the first 3 rows are actually the data for the same person with ID 1 across 3 time period 1, 2, and 3. And the next 3 rows are basically the ID 2, the same person, and across the 3 time period 1, 2, 3. And then person number 3, we have the data across the 3 time period 1, 2, 3. Okay, so sometimes we might have, like for example, an ID number 4, but we might not have the data across 3 time period. We might only have, for example, number 4, we only have a 1 and 2. That's it. So this is unbalanced. So this is could be happen sometimes in panel data. Okay. So the third column is called variable. So this is actually just a data for every single people across different times. So this is just a raw data we have. And then we can define individual mean. So what does the individual mean? So that's actually the mean for every single people, for every single individual. So we don't calculate for individual mean. We don't calculate the mean across different people. We just calculate the mean for one people over different time. So the first 3 rows are the mean for the first for the individual with ID 1. So for individual ID 1, we only have 3 data. So across time 1 to 3, so the average is basically 10. So this, and then we move to the next 3 rows. So this is the average for the second person. So this is across the time 1 to 3. And then we move to the ID number 3. We only have 3 data. So this is the average across 3 times for ID 3. So this is the individual mean. So this is the mean for every single person. Overall mean, that's very simple. So we don't care about the time, we don't care about the individual, so we just calculate the mean overall for all the data. Okay. And the next one, overall deviation. So what does it mean? Let's take a look on this. So we have the overall mean and we have the raw data. So this is actually a difference between the raw data and overall mean So basically, we don't care about the ID and time. We just calculate for every single data and the mean. So the difference between the data and the mean. And the next two are very interesting. The next one is called between deviation. So let's take a look on what does it mean. Between deviation is we're using this one. This is the individual mean minus the overall mean. So this is actually shows the difference between different people. We have overall mean across all the time, across all the individuals, and then we have quite different means for different people. So we can basically see how the people is distributed. Some people has their average value far lower than the total or overall average. And some people has the same, some people has a higher value than the overall mean. So this is actually, we can see the difference between every single, the average difference between every single person to the whole data set. And the next one is called within deviation. This is very interesting. So within deviation is actually, we're using every single data and minus the individual mean. So this is actually the difference over time for every single individual, because individual mean is the mean for every single person. So we would like to see how this person's performance across the time compared with his own mean across all the time. So we can see, okay, from time 1, 2, and 3, so this guy has the value and getting increased. So from -1 to 0 to 1, so the decrease is basically the difference between the average for this person is getting from negative to positive. And for this people, basically all the same. And for this people and the number 3, so actually, so it's getting better and better. So the next one is actually slightly different from this within deviation. So this is a within deviation plus an overall average. So this is actually a level scaled within deviation for every single. So this is a very interesting definition. So we can see quite different across individuals across the different times. Okay. So once we have that definitions, we can basically calculate the individual mean, overall mean, overall variance. So this is basically corresponding to the previous definitions. Okay. So now let's think about the data, the model. Okay. So we have basically 2 dimensions. So time and individual. So apparently we might have several different types of the model, because we have to consider both the time and the difference between time and difference between the individuals. So we basically have 3 types of model. So the first one called pooled model. So that basically means that we put all the data into one pool. We don't really care about every different single and every different single individuals. So we just consider every overall. And the next one is called fixed effect, and the next one called a random effect. So this is the corresponding to how the difference between individuals is fixed or random, is correlated away with one of the independent variable or not correlated. If not correlated, we call the difference between individuals are random. Okay, so let's take a look. So the first one is called pooled model. So the format is very, very simple, because we just assume we have a constant intercept and a constant slope. So basically, we don't care about all the difference between the individuals. So because we assume the trend across all the individuals are the same. So we have a fixed alpha, fixed beta. So this is actually how we're going to represent the whole data. So this is usually very restrictive panel data model. So most of the cases, we're not going to use this in the literatures. Okay. And the next one, if we consider the individual specific effect, so either fixed or random, so we're going to consider slightly different models. So if we consider the individual specific effect is correlated with one of the independent variables, we call fixed effect model. Or maybe we think about the individual-specific effect. That's basically the difference between the individuals are not correlated with one of the independent variable. We use a random effect model. So okay, let's take a look on the difference. So the first one is called fixed effect model. We assume we have the same slope across all the data, but for every individual, we have a different intercept. So that basically a scale for different individual. Maybe some people get really high capabilities, so the intercept is really high. But some people get much lower than the average level, so we got a negative one. So we have quite different, quite specific intercept term for every single individual. So this is a fixed effect model. And the next one is called a random effect model. So random effect model is actually, we add one more error term in here. So this is actually the alpha. So we consider alpha is one of the error term in here. And actually, so we combine them together as the total error. So because this is pretty random, so we're going to consider this as a part of the error. And so this error, covariance of this error is actually a fixed one. So we can calculate the correlation coefficient of the error, the total error across different time. So basically, and we define this as rho. So this is actually an indicator. And this is actually the fraction of the variance in the error due to the individual specific effect. So if this is actually 1, so that basically means the individual effect are dominating the difference or dominating the error. So let's take a look. So the alpha is actually this. So if we actually have the alpha so the sigma of the alpha is dominating this. So that basically means the error is almost 0. So that basically means, okay, so the most of the error is actually corresponding to the difference between the individuals. So, and this is the difference between the random and the fixed. Okay, so, but this is actually pretty abstracted. Let's take a look on stata and how we're going to using that. So actually, stata is I personally don't like stata, but actually stata is one of the popular tool to apply panel data panel regression. So usually people like to use stata to do the panel regression. So we're gonna take a look and see how we use this. Okay, so and if you log into Learn, so you will find out we have a file called, so the file called panel data model in stata.do. So do file, if you install do the stata, or you can go to the computer lab in the business school, and you can open this in one of the lab computers because the lab computer has been installed stata. So you double click on this, so you will have stata started and with one more window like this. So this is actually all the scripts we have to run the the data. So and this script is trying to use the data of this panel with underlying wage.dta. So DTA is actually a special format for stata file for stata software. So and usually let's take a look on panel wage and .csv. So let's take a look on how the data looks like. Okay, so this is the data we have. So this is apparently the panel data because we have ID, we have time. So let's take a look at ID. So first, several rows, we have ID 1. And for ID 1, we have the data across time 1 to 7. And then ID 2, we have the data across 1 to 7. ID 3, we have data across 1 to 7. ID 4 and across 1 to 7. So this is apparently the panel data. So for every individuals, we have experience, work, and so many different things, education and union, as a female or not. So this is a number of different variables, and for this is a log of wage, the log of salaries. We would like to run pattern regression using part of those X to see, can we explain the log of the salaries by using some of those and variables. Okay, let's close this. This is actually some scripts. So and we just introduced very simple scripts for Stata. So if you like to do something more study on Stata, you can basically check some of the materials or tutorials on the websites. Okay. So, and when you double click the do file and you open this, so it's actually very easy to run all the scripts. So if you like to run one of the lines, so you can just select the line. So you select the line, and on the right hand side, so there's a small button. So you move your mouse to the button. So there's a the explanation called execute selection. So you click on this. So you take a look on this. So clear all end of do file. So basically you clear everything in here. And the next one I set more off. So basically set everything to off. The next is use panel underline wage. So this is actually loading the data with the name panel underline wage. So because I put the data in the same directory to the do file. So if I double click the do files in here, so by default, so the working directory will be the same directory of this do file. So I put the data on the same directory of the do file. So if you're doing like this, you double click the do file and then you use the panel wage without extension. So basically the Stata will load the data into the Stata. So let's select this and click on this and take a look. So here we have several variables. So this is the variable we loaded into the data. So we have experience, work, occupation, industry, and residency, and marriage status, or female, education, and log wage. So and ID and T. Okay. So and this is actually loading the data. So the next one is actually called setting up the global variables. So global is a keyword. So so meaning of this one is I want to set up a global variable with a name ID. So I want to actually using this ID to represent an existing variable called ID the same. So actually existing variable is ID. So we just load it from our data. So but we created another variable which is a global variable with the same name, but that's actually okay. So the next one, I want to create a global variable T and represent the T's in here. And the next one, I want to create a global variable called Y list to represent our Y in our regression. So the Y is actually a log of wage, log of the salaries. And then I want to create actually an X as independent variables containing a number of different variables. So I want to combine them together as an X. So this is X list is a global variable. So the variables I want to use is experience. So it's experienced, and then experience 2. So this is actually experience square. So I have it here, and then weeks. So this is actually the weeks worked. So and ED is the education. So let's select them all. Let's click on this. Okay. So now I basically created several global variables, and then describe is actually a very general and tool to describe those variables in here, so we can see the basic information. And then basically I can summarize in detail of those variables, global variables I created. If you click on this, you will see, so this is a lot of information about every single global variables in here. So we have ID, T, log wage, of full-time job or experience, and weeks worked, and years of education or something like this. So this is a summary of details of those variables if you like to see. As we can also summarize the X without detail, so you can basically see. So this is a very simple summarize for all the independent variables. Okay. Now let's Next, let's try to set up the panel data. So before that, we can sort, but we don't need to sort actually. We can sort across the ID and also the time. So we can click on this. So we sort everything. And then the next keyword is XT_set. So XT_set is to set the panel data's X individual ID and the time ID. So X is corresponding to the individual, T corresponding to the time. So XT_set. So basically, is to set the individual IDs and the time for the panel regressions. So we're gonna execute this. So basically, you take a look on this. So now Stata knows we have a panel regression. A panel of variables is ID. Time variables is time. So it's strongly balanced. Okay, that's pretty good. And then XT_describe. So we can click on this. So so the Stata knows. So I want to basically describe the panel regression IDs. So we have ID and we have T. So this is actually the basic information. And I can also summarize everything again. So because we have identified ID and T as the panel. So basically we have all the informations in here for the panel data. Okay, so now the next one, we can basically do the regression. So the first one, I want to do the pooled regression. So this is a very, very, and very simple one. So to do the pooled regression, I just using the keywords regret. So this is actually a short for regression. So I want to regret Y and X. So this is very simple. So I don't care about the different individuals. I just assume all the trends are the same across individuals. So I just using a pooled regression. I select this and I click on this. Okay, and yes, and as very quickly we can get some results. So surprisingly, so we got very interesting results because we have the F value is very large. And so probability is very tiny. So that basically means R square is okay, but it's pretty low. And let's take a look on the P values. So all the, the variables has a very, very tiny P value. That basically means all the, variables are basically the significance for, the regression. So is it actually the truth? So we're going to try to run again. So the panel regression with a fixed effect. So the keywords is XTREG, XTREG. So this is actually the panel regression with the FE, the fixed effect. So if I select this and click on this, so let's take a look on this. Here now we have the F value very high. So the probability is very low. So that means, okay, so the overall R square, so is overall point this. That's actually not very good. But within the individual, that's pretty good. Between is very bad. So actually within the individual, so we can actually explain for every single individuals, but between, this is really bad. So actually we can observe quite good correlation for every single individuals, but actually between the individuals, we don't actually have the correlations. Let's take a look on the variables. So the p-value for weeks, that's very large. So that basically means, so this is not significant. So we can actually ignore this. But for the experience and experience square and education, so omitted actually. So apparently, if education is omitted, so that basically means, so this is actually really doesn't matter. So we don't need to consider this. Okay. Let's try to run another random effect. So basically the syntax is very, very much the same, but with RE represents for random and effect. If I run this, so basically we can see, okay, so this is a slightly different results. So we can have the probability very tiny, and we can actually have the experience weak is still very high. But for education and constant for all the others, so the p-value is very low. So that means experience 2, and education, they are all significant for the y. So this is a very interesting results. Okay. So Okay, so um, this is actually some of the results for the fixed effect. So we can take a look on one more things. Is the rho. So we just define what is the rho. So rho is actually explain. So what contribute to the error. So actually we have very high rho in here. So this is 0.97. So this is very close to 1. So that means the difference between the individual peoples contribute to most of the error. So that actually means, okay, so the difference between individuals are really high. So we might actually need to take care of that. So thinking about whether the difference between the individuals are correlated with one of the regressor or not. Let's take a look on the next one. So actually, we also has a pretty high and rows in here. So this is roughly 81. So that basically means that the difference between different individuals are still very high. So let's take a look on this. So the problem is that when shall we use the random effect? When shall we use the fixed effect? So this is really hard to do. So actually the good thing is we have a hypothesis testing called Houseman test. So this is to help us to actually to do and to determine whether we should using a fixed effect or random effect. So basically, we are trying to do the panel regression with a fixed effect and random effect again, and then we store their estimates into two variables, and then we're gonna run this Houseman test with the fixed and random results and see which one is better. So if we receive the probability of 0, so that basically means we're going to reject a non-hypothesis. So non-hypothesis is actually the unique error are correlated with the regressor. So the non-hypothesis is they are not correlated with regressor. So if they are not correlated, so we should using the random one. Actually, we reject, because this is a 0, we reject the not correlated. So that basically means they are correlated. So if they are correlated, so we're going to using the fixed effect and results in here. Okay. So the next topic, so it's a little bit advanced. So we're going to talking about the very normal problems in regression called endogeneity and exogeneity. So endogeneity and exogeneity. So this is a very, it's not quite easy to pronounce. Okay, so what is endogeneity and exogeneity? Okay, so let's assume we have actually simple linear regressions, and we would like to test the relation between x and y. So and ideally, we have assumption for random term. So usually the expected value for random term should be 0, and the variance of the error term should be a fixed value. Okay, so this is actually our assumption. So for the linear regression, the official assumptions should include actually 4 different things. So the first one is a linear regression, a linear relationship between independent and dependent variables existed. So if there are no linear relationship between x and y, so basically the linear regression does not make any sense. And the next one is called strict exogeneity. So we're going to explain what does it mean. And the next one is a spherical disturbance. And the next one is no collinearity. So collinearity is a serious problem in linear regression. Let's take a look one by one. Okay, so what is spherical disturbance? So actually this basically means the variance for the error should be fixed, should be a constant. So covariance for the error actually across different data should be 0. So this is actually the term for the error term, so the characteristics. Collinearity. So collinearity basically means one of the independent variables can be linearly predicted by other independent variables. So this is going to be a problem. So if you have a 10 independent variables, is one of the 10 could be predicted, or is a linear combination of the other 9 independent variables. So this is called collinearity. So this is going to be a very serious problem. So the collinearity might not necessarily to be the correlation. So if we have correlation between the variables, so that basically means we might have the collinearity. But if we have a collinearity, that does not mean so we have a correlation between the independent variables. So this is the problems. And the next one is called, so this is the most important one, called a strict exogeneity. So a strict exogeneity basically means the error terms, the mean of the error term across all the t, given any of the x, so the error should be 0. But the problem is that strict exogeneity is very hard to satisfy. So we might change this a little bit. So we picking up just one particular time, and for given an x at one particular time, we assume the error at that time is expected error at that time is actually 0. So this is called weak exogeneity. But sometimes even the weak exogeneity is very hard to satisfy in practice. So sometimes, in most of cases, we're going to having this for any of the time t. So we might have actually 2 possible reasons for this. So one of the reasons is maybe one of the predictor, one of the independent variables is correlated with the residue, with the error. So this is the problem. And another reason is that maybe we forget one of the independent variables in this linear regression model. And so, for example, if we like to forecast, or if we like to do the linear regression to identify one dependent variable y, but actually we should have 3 independent variables, but for some reason we forget one. So we only have 2, but that forgetted one is very important. So that basically means we cannot using 2 variables to explain our y. So we miss one of the independent variables. So that's going to be a problem. So this is also one of the reasons we have the weak exogeneity cannot be satisfied. So this satisfaction of exogeneity brings the endogeneity. So let's take a look on what is the reason for endogeneity. So probably we're going to forget one of the independent variables, and probably we have simultaneity bias. So this is really hard to pronounce. So simultaneity bias basically means we can explain y by using x, but at the same time we can explain x by using y. So explanatory variable is jointly determined with the dependent variable. So this is actually a very serious problem. And this is also one of the reasons we have endogeneity. And also maybe we have a selection bias. So the data is not random. We have just a particular group of data. And maybe, and so actually the data has some very important nonlinearity. So we forget nonlinearity. So this is all the reasons for endogeneity. So in addition to the reason, so we would like to have, that's the theoretical reason. We would like to have some examples in here. So for example, if we like to explain the salary, so we might like to use in the years of education as a predictor. So that sounds reasonable, but the problem is that so the years of education might not be the true reason for the salary. So the true reason might be the ability or the work ethics. So that's probably the reasons. And years of education is also correlated with ability. So that's going to be a problem if we forget ability and we only use a year of education to run a regression for the salary. So that might be cause endogeneity. And another example is that what if we would like to explain or forecast or run a regression for the probability of divorce by using the employment status. But the problem is that employment status might be correlated with the economy. For example, in in a financial crisis, so the probability of divorce getting very high. So what is the reason? So it looks like it's an employment status, but actually is the economy cycle. So economic shocks is actually the real reason behind the divorce. So this is actually the real reason. And actually, the next example is about graduation rates for different schools. Um, Maybe we can say, so the fraction of the budget is very important, but actually fraction of budget is correlated with the political results, political factors. So and what is a real reason behind the graduation rates? If we're only using a budget or a fraction of the budget, so this is actually cause endogeneity. We cannot explain why sometimes the graduation rates and the budget, a fraction of budget cannot explain the graduation rate. Probably because we have the different parties or different economy, different and governments and different policies. Okay. And the next one is if we like to estimating demand for appropriate price. So this is going to be a problem because the demand and price are determined and simultaneously for each other. So because the demand determine the price, but at the same time, price also determine the demand. So this is actually the simultaneously and determine. Okay. So this is our quite typical examples for endogeneity. And to solve the endogeneity, so we have a number of different methods. So the first one, I personally believe might be the best one. So, and this is called the natural experiment method. So the natural experiment or natural event method is actually trying to catch some of the natural experiments or natural events. So these events are very, very special, or it's very random. That could be randomly splitting the data to two groups. And so because of this event, so probably we can explain more on the why, or we can explain more on the dependent variables. So sometimes it's not very easy to find those events, but we're gonna need to try to analyze the the business or the data and try to find out what is the special event. For example, like the example previously, so if we like to explain the wage by the education, so we know that we might be able to using education as one of the independent variable to explain the salary, but actually, the salary is actually strongly correlated with the unobserved ability. So the education is also correlated with the ability. So maybe we can use another, variable called times of promotion, if possible, because times of promotion, so it's actually a very good indicator for the good salary. And times of promotion can be an event. The promotion is an event. So if somebody got a lot of different times of a promotion, so this is a very obviously indicator that he has very good capability, very good ability to earn very good salary. So this is actually correlated with the education, but might not be 100% determined by the education. So we might add one more variable called times of promotion, and this variable actually randomly split the people to two groups. So some people does not have don't have a lot of promotions, but some people does have. Okay. And the next one is the probability of divorce. So apparently we can add a financial crisis as a control variable and using the data across 2008. So probably we can run a regression using the data from 2005 to 2010. So across the financial crisis. So and we're using one more control variable to control whether we are in the financial crisis. So maybe we'll find out a control variable contribute a lot on the probability of the divorce. And the next one is explain we would like to explain the graduation rate for a different school. So maybe we can add re-election as a control variable. So maybe when the whole district has a re-election, so maybe something change for the budget. So actually we can have observed different graduation rate. So this is actually a popular method for endogeneity. So I believe in practice, so most of the cases we need to do something like this to try to avoid or try to solve the endogeneity. And the next one is called the difference in difference method. So this is particularly on, so what if we would like to compare the difference for some change, for some events. So for example, we might like to say maybe school district is very important for the property price. So to prove this, so we might need to run a regression. So a very good example for difference in difference is that we can choose two areas, A and B. So maybe for A, before A and B, before 2016, neither A or B is a school district because they don't actually quite close to a good school. But at 2016, a good school has been built in area A. Okay, that's pretty good. So we can basically calculate the price difference for A before and after the school has been built. And we can also calculate the price difference of B before and after the school has been built. So we can assume maybe the difference of A is pretty large, but the difference of B maybe is not that large. So we can calculate the difference of the difference again. So we can try to calculate the difference between difference of A and difference of B. And then we can try to run a regression across the two, difference. So XA is a control variable. So if we are in the X area A, it's 1. If not, it's 0. Time, if before 2016 is actually 0, after is 1. So we can using D and with the two control variables times together. If they are both 1, so they are actually the control in the area A and after 2016. So actually we can have a D, and so we can basically find out how D is contribute to the housing price. So this is a very typical example of difference in difference. But in most of the cases, it's really not easy to do differences in difference. You're gonna have to design everything careful. Okay, so the last one is called instrumental variable. So instrumental variable is probably most widely used method for controlling endogeneity, but it's actually not very easy to do. So the idea is to find an additional variable, which is an independent to the error term, and but correlated with the independent variables. So we can use the instrumental variables in the regression. So this is actually embedded. So one of the functionality embedded in Stata. So we are not going to introduce in here. So if you are very interested, so you're gonna take a look on the Stata documents. Okay. So this is everything for regression. So we covered the linear regression, we covered the panel linear regression, we covered some important and slightly advanced topics, endogeneity and exogeneity problems in linear regression. So I strongly recommend you to practice some panel regression by using Stata, because then you can download the scripts and data and try something in Stata. And also try to do linear regression in Excel and see how it works. Okay, thank you.